Okay, today we shall have a look at what is the meaning of a bias in a neural network. So far we have seen McCulloch-Pitts neuron model in which we have not used a bias, we have only used a threshold. And now we are interested in knowing the function of this bias. So we have considered a neural network here, and in this particular neural network, as you can see, what happens is that there are inputs x1, x2, x3 up till xn, and there are weights. So this input is having a weight w1, w2, w3 up till wn. These are the weights. Usually I have not denoted the weights in this particular form. These are not neurons, these are weights. So here you can see one more input which is there, which is called as the bias. So this is bias. Usually what we have is that this particular summation, this is nothing but the summing function, and this is nothing but the activation function. So what happens in the summing function? We take summation of xi wi, that is the input into the weights. So this is what we call as net. And then activation is this net, whatever we get here at this particular point, we give it to the activation function, which is nothing but any function which we have seen earlier, and you get f of net. Now, and this activation function will finally be producing your output, which is O1 or whatever. So now what is this bias? Besides these inputs which we have considered here, we have some other input which is given here, that is called as bias. So bias is an additional parameter which is used in a neural network that requires no input. So there is no input associated with this bias. So now if at all you see here, these particular inputs which are nothing but the sum of external, these are external inputs, and net, whatever we calculate, it is nothing but the sum aggregate of external inputs. So sum aggregate of external inputs. Now this, only the external inputs earlier were able to we were to calculate summation. We were using only the external inputs, and this was used to fire the neurons. But what about internal? There is something, an internal bias or the internal input which is present within the neuron, which will allow the neuron to be fired or not. So this input is used to adjust the output along with the weighted sum of the inputs. So along with this external input, this bias which is internal to the neuron will be affecting the output. So initially your output was nothing but only f of net, but now the output will be taking net plus b. So now usually, although now I am calling it as net plus b, but later on whenever we calculate net, the term will already be included. It will become xi wi plus the bias term. Also, this bias can be assigned a weight. So if at all bias is b, I can assign a weight which is w0 for the bias, and that weight also, so my new net will be it will be summation of xi comma wi. The new weight will be new net will be summation of xi wi plus b times the weight w0. So I will just explain this to you. So if at all we have considered this neural network with n inputs and weights w1, w2 till wn. So at this particular point we calculate the net here, and then this is the activation function which will be producing f of net. Now here, this is a simple neural network. Now if at all we want to introduce You know, you all have studied the gates, etc., which you all have studied. Now, what I have used there is we have been considering the net. Net is nothing but summation of I is equal to 1 to n. Sorry, summation of 1 to n xi wi. So this we were calculating. But now this is the aggregate activation from all the external sources. Now if at all we want another input which is say internal to this, and this we call as bias B, and this one will also have a weight. So new net will be summation of I is equal to 1 to n xi wi plus this particular bw naught. So either you can consider it within the net or you can consider it outside the net. So this is your new net including the bias. So you can consider, so this extra term is added. Now what will happen to this extra term is that, see, sometimes this is called as net and this is the extra term. So, you know, and this weight usually can be assigned as W naught is equal to 1 also. It depends. So now what is the function? So most of the time this is used so that the activation function can be varied. Now why activation functions need to be varied? Now we have seen the different activation functions and we have seen that most of the activation functions which are there, what happens to these activation functions? Most of these activation functions will be centered around 0. So you take your TLU function, threshold logic unit function, it is centered around 0, and here it is, we'll take one example of threshold TLU function, threshold logic unit function. So what is the f of net of it? F of net is equal to 0 for net is less than or equal to 0, and f of net is equal to 1 for net is greater than or equal to 0. And this one is only less than 0. This is greater than or equal to 0. So as you can see here, this activation function is centered around 0. Now if at all, most of the times if at all you have seen this particular activation function is centered around 0. Now what we have done whenever we have designed the gates, if at all you see the design of OR gate, or if at all you see the design of AND gate, if at all you see the design of say NAND gate, etc. What is the threshold which you have got there? Now this TLU, threshold logic unit, the threshold is fixed, it is equal to 0. But whenever we have designed the gates using Maculop-Pitts neuron model, you will see that for a 2-input OR gate, the threshold is 1. For a 2-input AND gate, the threshold is 2. Similarly, for a NAND gate, etc., the threshold will be NAND gate, the threshold is equal to -1. NOR gate, the threshold is equal to 0. So what happens is that the threshold is varying every time. But these activation functions which we have studied, almost all the activation functions are centered around 0. Now this we first consider, if at all you consider a sigmoidal function. Sigmoidal function also will be centered around 0, like this. Now if at all you want to shift this particular function now, for OR gate, as you know, threshold is equal to 1, AND gate threshold is equal to 2, NAND gate threshold is -1, NOR gate threshold is equal to 0 using Maculop-Pitts neuron model. What is done is that rather than changing the threshold every time, we use a parameter called as bias. And this particular parameter bias will shift the neuronal activation functions either towards the left or towards the right. So that means this value can get shifted this side or it can get shifted this side. So either you shift it this side or I use a different color or you shift it this side. Is that clear? So similarly, this activation function also would be not centered around 0. It will be coming towards the left like this. Similarly, the function somewhat like this. So basically, if at all you want the function to be shifted towards the left and towards the right, you will be using the bias. Is that clear? So the work of bias to shift the function, activation functions which are usually centered around 0, to shift them either towards the left or towards the right. That is the role of the bias. So what will happen is that, supposing we take a particular function, we'll take this, we have taken the example of TLU function. So if at all we take the example of TLU function, so again I draw the same function, net, f of net, and it is like this. Now with this equation, f of net is equal to 0 for net is less than 0, f of net, sorry I wrote f of net is equal to 0 for net less than 0, f of net is equal to 1 for net greater than or equal to 0. If at all I use a bias, what it will be is that if it will be f of net plus b, or I write it as b, usually later on we will be writing it as net only, but as of now I write net plus b, it is equal to 0 if net plus b is less than 0, if at all it is equal to 1 when net plus b is greater than or equal to 0. So when this net is introduced, what will happen is that, supposing that our bias is 3, supposing that our bias is 3, so we select a bias b is equal to 3. So what will happen to this? This particular output f of net plus b will be equal to 0 when net is equal to 3. So what will happen to this? Net plus 3 is less than 0. So net will be less than minus 3. So when net is less than minus 3, and it will be equal to 1 when net is greater than or equal to minus 3. So this we get from here, net plus 3 is greater than or equal to 0, so net will be greater than or equal to minus 3, like this. So I'll just erase this part and this part. Okay, so what is happening is that this function which was centered around 0 here, now the same function will be centered around not 0 but around a bias value that is 3, but not around 3. It will be centered around minus 3. So how will be the graph? The graph will be like this, and this value is minus 3. So if at all, now which side you have shifted? This is right side, and this is left side. So if at all you want to shift the function, activation function, towards the left hand side, you have to use a positive bias. We use b is equal to 3, positive bias. And if at all we want to shift the function towards the right hand side, we need to use negative bias. But before that, have you seen that what is the range? What is the range of this particular function? The range of this particular function, now this particular range of 0, range for 0 output, now this one, this function, range for 0 output was what? Range for 0 output was 0 to minus infinity, and range for 1 output was what? Sorry, we write it as minus infinity to 0. So when I use these brackets, I hope you know that both are not included, 0 is not included, and here it is 0 to plus infinity. So 0 is included, so I put a square bracket. Infinity is not included because we did not put infinity, so infinity. So this is the range for 0 output and range for 1 output for this particular function, normal TLU function. But now if at all we move on to this shifted function with a bias, what will be the range? The range of this particular function, range for 0 output will be what? 0 output will be from minus infinity to minus 3, and range for 1 output will be from minus 3 to infinity. So this is this is your positive range and this is your negative range. So what you can see here, this range here is equal. This is 0 to infinity, minus infinity, this is 0 to infinity. So equal range. But what happens is that here, for one output you have much greater range as compared to the 0 output. So what happens is that it is biasing. The neuron is biased towards one output. The neuron gets biased towards one output. So that is the reason we call this term, we call it as a bias, because the introduction of a bias in the neural network will cause the neuron to be biased towards any one of the outputs, either the lower output or the higher output. That is the reason we call it as a bias. Now I have not, you can put it down in words and you can write it. Is that clear? So this is the importance of bias in the neural network. So what we can see here is addition of positive bias is equivalent to shifting the function to the left. So the function is shifted towards the left, that is this side, and if at all we add a negative bias, the function will be shifted towards the right side. Now it is just a role of bias in a neural network. Okay, I have already told you bias value allows you to shift the activation function either to the left or to the right. Bias only influences the output, it doesn't interact with the input. So it is not going to change the input, it will only affect the output. Now it is just like an intercept added in a linear equation. So if you remember your equations, now it is like y is equal to mx, right? So this is an equation, y is equal to mx. Sorry, this is x and this is y. This is y is equal to mx. So what you have is that there is an intercept which is added. Y is equal to mx plus e. So that means the equation shifts like this, right? So this is nothing but y is equal to mx plus c. So similarly, the equation is basically, now here the equation is centered at 0. And here the equation changes. The line with the equation changes. Because of this intercept, y-intercept, which is c. Similarly, what we have seen is that the activation function which was centered around 0, that activation function will be changed here in this particular case. Example is, if at all any activation function is centered around 0, okay, we have seen, we'll take a bipolar sigmoidal function. If at all it is centered around 0, what happens is that you can shift the function by using a bias term. You can shift it towards the left or towards the right, so your function will get shifted. Now in this case the function is shifting towards the left. So the bias is, say, negative value minus 1. So it is centered around plus 1. So in this way, so this is the role of the bias. So now we have some problems to be solved using a bias. So all these gates, whatever we have studied, AND gate, OR gate, NOR gate, NAND gate, we will be implementing them using a bias. So which is a better practice rather than using every time a MCP neuron and use a threshold, a variable threshold. A better practice would be to use a bias instead to design the neural networks. Is that clear? So we shall implement neural networks using bias. Okay, we have already discussed the logic gates using Maculop-Pitts neuron model, wherein we have only considered the threshold. But now, as we already know what is a bias, what we will be doing is that we will be also introducing the bias term in the equation of the gate. So, if at all this is the neural network and the bias which is given to it is B. So there are two inputs, x1 and x2, with a weight w1 and w2. So here usually what we calculate is that we calculate the net and the output f of net is calculated here. So while doing this net, previously we have considered only net is equal to x1 w1 plus x2 w2 or xn wn. But now what happens is that we have to also take into consideration this particular term, that is the bias term which is added. So we have to add the bias, and if at all you want, you can assign a weight to the bias also. So the weight times the bias also will be added. Now the threshold is fixed for this, that is t is equal to 0. And when threshold is fixed, we have to check whether this particular net is greater than or equal to threshold. If at all net is greater than the equal to threshold, which is 0, then f of net will be 1, and if net is less than threshold, then f of net will be equal to 0. If at all it is unipolar neuron. If at all it is bipolar neuron, then what will happen is that f of net will be equal to, what will happen if at all it is a bipolar neuron? If it is a bipolar neuron, then f of net will be equal to +1 for net is greater than or equal to t, and if at all net is less than t, then f of net will be equal to -1. This is for bipolar neuron. Okay, so now we shall have a look at the first gate, that is OR gate using a neural network. So in an OR gate, we shall consider the two input OR gate, and similarly we shall take the AND gate, two input. Now for a two input OR gate, what is the output? What is the expected output? This is the truth table which I have drawn. The output for 0, 0 is 0. For 0, 1 it is 1. 1, 0 it is 1. 1, 1 it is 1. So if at all we consider the model which was shown previously, we can calculate net. And the weights, assuming that the weights will be positive weights, because we know that for all gates we use positive weights. So if at all I consider the model, only difference is that we are not considering only two inputs, x1 and x2, we are considering a bias also. So weights, because it is an OR gate, as we have considered previously, the weights I assume to be 1. And with these weights assumed to be 1, what will be the equation for net? If at all we do the summation here, and net I will write as the summation plus b. So this will be x1 w1 plus x2 w2 plus b, and what is this? x1 plus x2 plus b, because x1 and x2 both are because w1 and w2 both are 1 1. So first we shall calculate this particular summation, that is net, and here, okay, I have already included this. I shall write it as net plus b and not net, and then I will calculate net plus b. So net will be only this part, x1 plus x2, and b we shall take it separately. If at all some of the textbooks take b along with net, some of them write separately, so we shall take it separately, because for me I wanted to show the difference. So here, what is net? Net is x1 plus x2. So 0, 1, 1, 2. And what will be net plus b? That is net plus bias will be 0 plus b, 1 plus b, 1 plus b, 2 plus. Fine. Now, what value of net should be selected such that this net plus b should cross the threshold. So see here, when it is 0, 0, the output should be 0. But for these three outputs, the expected output is I. So net plus B should be less than 0 for which condition? This condition. And net plus B should be greater than or equal to 0 for these three conditions. So this I will write here only 0 plus B should be less than 0, 1 plus B should be greater than or equal to 0, this should be greater than or equal to 0, this should be greater than or equal to 0. So if I take the first equation, 0 plus B is less than 0. That means B should be less than 0. And then what I get is that second is 1 plus B should be greater than or equal to 0. So what should be B? B should be greater than or equal to minus 1. And the third one is 2 plus B is greater than or equal to 0. So B has to be greater than or equal to minus 2. So these are the three conditions which have to be fulfilled. B should be less than 0, but it should be greater than minus 1 and minus 2. So if at all I draw the line, x-axis and y-axis, now this is for the bias, this is 0, this is minus 1 and this is minus 2. So B has to be less than 0, meaning it should be this side. And then I say that B has to be greater than or equal to minus 1. And then the third condition is B has to be greater than or equal to minus 2. So all these three conditions should be satisfied. So in order that all these three conditions are satisfied, where should be B? The value of B should be lying somewhere here. So any point I take here, now B should be lying between minus 1 to 0. So I select bias to be equal to minus 0.5. If you want, you can select minus 0.7. If you want, you can select anything else. So we select B is equal to minus 0.5. Now with this B, we again calculate net plus B. So what will be net plus B? Net plus B will be, in first case it is directly B. So it is minus 0.5. Second case it is 1 plus B. So it is 0.5. Third case 0.5. Fourth case it is 1.5. Now let all you see here, only this first value is negative, rest all these values are positive. So that means when we calculate f of net, what is f of net? F of net will be 0 if at all net plus b is less than 0. And if at all net plus b is greater than 0, that is here, the answer will be 1. So we get 0, 1, 1, 1. So by using this, we have designed an OR gate, and this is the OR gate which is designed here. So I will just so finally we have, this is the OR gate which is designed, and the bias is selected as minus 0.5. So if at all you select the bias as minus 0.5, you will getting the output as 0, 1, 1, 1, which is same as that of OR gate. So now the next is, we shall check the other gates also, AND gate, NOT gate, and NAND and NOR gates. Now we shall see how to implement an AND gate. So first step, draw the truth table. We know the expected output for an AND gate, and the expected output is 0, 0, 0, 1. And if at all we consider the previous, just how we have considered for the previous one, what we have done is that we have taken a simple network. X1 and X2 are the inputs, W1 and W2 are the weights, and So B is the bias and the weight assigned to the bias B is 1. Actually I can assign anything, but as of now we will be assigning the weight 1 because for these weights are also 1, W1, W2 is also equal to 1. So what will be the value of net? Net, as you know, will be x1 W1 plus x2 W2, and it will be, since W1 W2 is equal to 1, it will be x1 plus x2. So we get the value of net 0, 1, 1, 2. Now as we know that the threshold should be such that it will divide this. So the first three inputs should be 0, 0, 0 and the next input should be 1. So if at all I calculate net plus b, it will be x1 plus x2 plus b, that will be 0 plus b, 1 plus b, 1 plus b, 2 plus b. Now as you know that the output will be 0, 0, 0 for the first three cases, so I should write that 0 plus b should be less than the threshold. The threshold which I select is t is equal to 0, and only the last one should be greater than the threshold, that is t. This threshold is nothing but, if at all I want, I can write it as 0 also. I can replace it and write it as 0, 0, 0, 0. So for this first condition, for it to be according to the first condition, b should be less than 0. According to the second condition, 1 plus b should be less than 0, so b should be less than minus 1. So if b is less than minus 1, it is also less than 0. So we can ignore this condition. The second condition is 2 plus b should be greater than or equal to 0, which means that b should be greater than or equal to minus 2. So if at all we draw the line, it is 0, minus 1 and minus 2. So b should be greater than or equal to minus 2, this side, and b should be less than minus 1, so this side. So I select the value of b is equal to minus 1.5. You can select minus 1.7, minus 1.2, anything you can select. So the value of b will be minus 1.5. And here you will get the output O. So what we have designed is, we have designed an AND gate. So this output will be 0, 0, 0, 1. Is that clear? Similarly, we can design an AND gate and an OR gate. So finally, this is the answer. You are asked to design an AND gate. So this is what finally you will be designing. Now if at all you want to make a change here, I can change this. This I can put minus 1.5, that is the weight, and bias I can keep as 1. So this can be interchanged. The bias value can be 1 and weight can be minus 1.5. It is one and the same. So that also will work. Is that clear?